Yes, good morning. Here we are. It's the physics video lecture, physics 105B, video lecture 39. We're back to Hamiltonian mechanics. I decided to add one more important topic. And so I can even give an outline of the significance of this whole section on Hamiltonian mechanics. So we'll tackle one more thing. So you could say the first thing was just as another method of solving the equations of motion. But when we finally get to H, Q, P, and T, that's the form of classical mechanics that quantum mechanics, in particular non-relativistic quantum mechanics, is going to refer to. So for that reason, we have to know about the Hamiltonian and the Hamilton's equations of motion, which I'll go ahead and write here as well. Q dot PHP, P dot PHDQ. This one gets the minus sign. Okay, so that's the one aspect. The second aspect, and let's go ahead and write, if we're talking about quantum mechanics. The second aspect is phase space, and some of the interesting formalism that goes with that. You know, I may have forgotten the name of a really important theorem. UVA. A lot of physicists call that Louisville, but that's not how it's pronounced. Take it up with the French. But Leuvier's theorem, we did talk about. It is that the phase flow preserves volume, or the phase fluid is incompressible. Phase flow preserves volume. We did an interesting proof of that. I have, just in terms of incompressibility, I still owe you some fluid mechanics for that. Be that as it may, this is used in quantum mechanics as well, and statistical mechanics. And statistical mechanics. So there are references made to this, and you want to have seen it here before you hear about it elsewhere. And a third aspect is what we're going to do today. Poisson brackets. Poisson brackets, and again, that is referenced in quantum mechanics where it is called the commutator. That's the classical analogon of the commutator. So again, good. So this is what we're going to talk about in this hour, and we don't have to do that much with them, but we want to see them and know what they're all about. So let's have a go at it. We just assume that we're working with a Hamiltonian system. So for Poisson brackets, we have H of Q, P, and T. Okay. Working with a Hamiltonian system. And now we'll consider some function of the coordinates and momenta. So, and let F equals F of Q, P, and T be a function of the coordinates and the momenta. That's redundant, but let's go ahead and say it. And momenta. Now, of course, the Hamiltonian itself is an example of this, but other constructs, linear momentum, angular momentum, are also functions of the coordinates and the momenta. And so now what we're going to do is look at the complete time derivative of this f. So next, take the complete time derivative of some function of the coordinates and momenta, and we have sum over partial f with respect to q sub I, qi dot, and the same thing for the momenta p, because we're just doing a chain rule, plus pf v pi dot. Okay, should have written the, okay, that's all right. And then the explicit time derivative outside of the summation. Well, we have Hamilton's equations, so this can be written partial f partial q sub I. Remember, qi dot is partial h partial p sub I, and then we have plus partial f partial p sub I. P sub I dot is minus partial h partial q sub I. So negative partial h partial q sub I. Well, we can pull the df dt. We can pull the minus sign out front here. But this is the definition of Poisson bracket f h, and we'll write q p because that's the order in which we took those derivatives. So p f b p. So actually I'll write this here and put a box around it. A colored box while we're at it. Okay. So this is called the Poisson bracket, this big collection of stuff. Okay. Okay, what's next? We next consider the case, well, I'll put this here, Poisson bracket. And now since this was some function of the coordinates and the time, the coordinates and the momenta, we can think about a function or a combination of those things that is conserved. So if it's a conserved quantity, we also call it an integral of the motion. Okay, so suppose f is a conserved quantity integral of the motion. That's just some terminology. So if that's the case, then we've got a zero here, right? And then we would have FHQP plus partial f with respect to t is equal to 0, and the important case where f is not explicitly a function of t, and f, the way I like to write it, is not explicitly a function of t, then we just have this Poisson bracket is equal to 0. So this is a way to find and evaluate conserved quantities. If the Poisson bracket with the Hamiltonian vanishes, then you have a conserved quantity. I'm going to give an example of that right away. we can see how that looks in practice. So let's look at the Hamiltonian for the central force problem. There we know about the conserved quantity. And we'll see explicitly how that works. So our example central force. And here we have the Hamiltonian piece of r squared over 2m plus piece of phi squared over 2mr squared plus u of r. That's the Hamiltonian. And now what we want to do is write out what this Poisson bracket would be. So I'll write it in the abstract form, and then we'll, in terms of P's and Q's. So we have, and we know that P phi is constant, comma, because phi is cyclic. Okay, so that's something we know. Now just FH once more, sum over the F Q sub I and then minus df P sub I dH dQ sub I. So we got to translate that into what we have right here. So what we're going to write is P sub phi and H. There's our Poisson bracket. We'll just do them one at a time. So we have D P sub phi D R. Okay, the two Q's are R and phi, right? So actually I could write, we'll do that. P sub phi dr, dH, d P sub r. And then we have a second one, d P sub phi, d phi, dH, P sub phi. And then the other two we're subtracting off, so d P sub phi, d P sub r, dH, r minus d P sub phi, d P sub phi, dH, d phi. Okay, so that's how that translates. And what do we get here? dP sub phi dr, so we get a bunch of trivial zeros right there. dP sub phi d phi also equal to 0. dP sub phi del P sub r also equal to 0. This is the only one that is equal to a 1, but dH d phi is equal to 0. So the whole thing is equal to 0. And so that's the explicit calculation for showing that P sub phi is constant. Well, we knew it already, that's why we chose to do it, but here's the explicit calculation there. So there are some rules, some general rules that hold for these Poisson brackets so that you don't always have to write out the whole thing. And that's what we'll look at next. Oh, actually, before that, before the general rules, the Poisson bracket can be defined for just a, instead of the Hamiltonian purely here, it can be just defined for a second function of the coordinates and momenta. So that's what we'll write down as its more general definition. So Poisson bracket for f of q and p, g of q and p. And in fact, we can put the time in there as well. G of q, p, and t. So now we have the same definition as we did here, except instead of h, we have g. So we have f, g. By the way, you don't always have to write this there, but I'm just noting it. Different books will have a different definition. You put the p first and the q, then it'll also reverse the minus sign. It'll be the same. It'll be the same object. Okay. So yeah, we have the sum, the f, q, the g, the p sub I minus the f. Q sub I equals 1 to n. And there are some properties that are actually pretty trivial, but I'm going to have you guys calculate, so we'll make this a basic little homework problem. I'll have you guys calculate the following. Show that one f p sub k is equal to df dq sub I delta ik. So the Poisson bracket of f with p sub k, and then the Poisson bracket of f with q sub k is minus df dp sub I delta ik. And those are going to fall right out of these definitions, of course. Okay. But these next two, actually I'll skip a couple. These actually go together, so we'll just put them all under sub 3 here. P sub I, q sub k, minus delta ik. P sub I, P sub k, 0, q sub I, q sub k, equal to 0. So these are called fundamental Poisson brackets. Nothing difficult, but that'll give you a little chance to work with them. And let me see, I've got nothing but time. I have one more. Yeah, and one more application. So we'll call this homework. This is very basic. There's another interesting application. And these are things you're going to see, and you're going to see analogous things to these. So very good to work through them right now. So the other thing I want to do is just a one-dimensional solution of Hamilton's, or a solution of Hamilton's equations for one coordinate using Poisson brackets. And I'll skip a ton of other interesting stuff. Can't do it all. Solving Hamilton's equation. Well, we're just going to solve it for a really simple case, but we're using the Poisson brackets, so that's of interest. And so let H equal H, Q, and P. And we know that F equals F, Q, and P, and we have dF dt is equal to F comma H. Okay, so that's our Poisson bracket. No explicit time dependence. Now let F of Q and P, F of Q and P be Q itself. Okay. Because then we have Q dot is equal to F Poisson bracket H. And okay, I'll leave that there for a moment. The solution that we're looking for, the solution that we seek is Q of T equals Q0 plus T times dQ dt evaluated at T equals 0. T squared over 2 I'm just writing the Taylor series out, right? Higher derivatives as well. So we're just looking for a Taylor expansion. And what we're going to do is just keep taking time derivatives of this object right here with dq dt evaluated at t equals 0 is just f is just qh evaluated, at t equals 0. E squared q t squared is going to be this qh Poisson bracket. Since it's the next derivative, h, etc. So if we had a full infinite series, we would need an infinity of these things. And it looks like it could get a little complicated, but there are cases where this works really nicely. So we'll write down the third one. Yeah, we'll write down the third one just to make sure we see what's going on here. Third derivative is going to be this QH Poisson bracket H bracket with H again, and so forth. So I'm going to assign just a really basic one, and you'll see what happens. So again, it'll be a problem that we know really well, namely free fall. Okay. So as a homework problem, okay, so we have these here. It's actually kind of fun, you'll see. homework. Solve our free fall problem using this method here. Okay. And here's how this will look. H is going to be P squared over 2M, right, plus potential energy, which we're just going to call plus mgq. Mix up your G and your Q there. Okay. So there's our Hamiltonian. And the nice thing is we know the solution here. So what we expect to happen is that the solution here will be truncated actually at this one here, because we know free fall just goes to T squared, and all higher ones vanish. Okay. And I'll just put here an interesting bonus. You know, if you need something to do, harmonic oscillator. Because if you do the harmonic oscillator, we know that the infinite series goes all the way out to infinity, and we're not going to be able to just declare all these equal to 0. By the way, you're not going to declare it equal to 0, you're going to find that it's equal to 0. And once one of these equal to 0, all the higher ones are trivially equal to 0. But with a harmonic oscillator, we know the power series, sine, cosine, or both of them, are both infinite. But if you want to tackle that, I'll tell you what you'll find. Plus 1/2 k q squared. What you'll find is after about the 4th or 5th one of these, they repeat themselves. Okay, and then with careful summation, you'll actually only have to do 4 or 5, and then you see how they repeat themselves, and you generate the sine and the cosine pattern. But that's if you're wanting to do it. Make sure everybody does this one. And good. So we'll leave it at that. And I'm not even quite sure what we're going to do, except that I know we have to tackle some fluid mechanics in the coming last week or 2, week and a half. Okay, see you later.